Hi, this is Richard C. I'm a math tutor here at Wyzant, answering questions submitted by a student. This has to do with exponential growth. And because it's a question involving populations, we are assuming continuous growth. The formula for continuous growth is the ending amount A is equal to the beginning amount P times e to the RT, where R is the rate of growth and T is the time elapsed. We're given 2 points here. The starting point is in 1995. The population was 3,610. And then 17 years later, the population was 5,202. And we just need to fill in, we need to calculate P and R here based on these 2 data points. Well, this first data point gives us the starting amount, obviously. And P is the starting amount. When time is 0, this term disappears. This just term becomes 1. So you have 1 times P here. So we can put that 3610 right in there. To get R, what we're going to do is just use this second data point. And you can see I've got 5,202 as the population. And then R is T is 17 here. And then we're going to solve for R by taking the logarithmic form, writing this equation, which is an exponential form, and rewriting it in logarithmic form. I'm assuming that's something you know how to do, and if you don't, you need to review your log and exponential forms of the equation from Algebra 2. Typically, it's covered in Algebra 2. Anyway, so we get, for R, we get 0.0215, and so this is our equation, our model for the amount of people after T years have elapsed from the starting time, which was the beginning of 1995. So now we have the model to use, and we're going to apply it and answer the question. So the first part of the question says, well, what was the population at the beginning of 2019? Well, 2019 minus 1995 is 24 years later. So we just replace T with 24, and of course we know the starting amount was 3610. And I put that into my calculator, and I'm getting 6046 as the population in 2019, at the beginning of 2019. And let's compare that to the population at the beginning here of 2012. This is 2012 here. And you can see it's grown. We started in 1995. You always want to look and make sure your answers are reasonable. So this was a jump of 17 years, and it didn't double yet. But then another 7 years, and it will cause it to finally double, not quite double the original amount. So this seems like a reasonable answer. Now, part B is how long from the beginning of 1995 will it take the population to reach 9,000? So we're given the ending population, and we're going to use the same formula, 3610 e to the 0.0125, except now we have to solve for T. So we start by getting rid of that 3610. So I'm going to go 9,000 divided by 3610, 2.49. equals e to the 0.0125t. Now again, we write this exponential equation as a logarithmic equation. We'll get the natural log of 2.49 is equal to 0.0125t. And we divide both sides by 0.0125. So let me start with the log. Put that into my calculator. I'm going to divide that by 0.0125, and it's going to give me 73. And they want 2 decimal places, 73.08 years. So if we wanted to think of it as another data point, this is 24 years. It'll take quite a long time, 73 years, to reach 9,000, which seems reasonable. It would be roughly triple the starting amount, and this is growing very slowly. As you can see, it took 17 years to just go from 3610 to 5202, and then 7 more years to go to 6046, and we're saying it would take 73 years altogether to get to 9,000. That seems reasonable. And then part C, what year did the oh, we are there, sorry. 2019. That's A. How long? Oh, C is just the population. It's just going to be 73. So it's 1995, sorry, plus 73 years later. So that's nice. So it'll be 2068. So in the year 2068, at the beginning of that year, which is 1995 plus 73 years. So it would be the beginning of 2068, the population should be 9,000. Okay, so that's it. A, B, and C, we're done. And this is a nice problem. It's fairly complicated, reasonably, it's I'd say mid-level in difficulty, and you'll see this sort of thing all the time. By the way, PERT or PERT is continuous growth, and that's the exact formula that we use throughout the pandemic, by the way, to estimate the infection rate and the number of infections and so on. And there was a lot of math going on during those years, and they were very unpleasant years, but it was a good learning opportunity for people interested in exponential growth. Anyhow, that's it. I hope this was helpful to you. I'll see you again next time. Bye-bye.